this week in lab, we are doing the much anticipated experiment 8, the Grignard reaction. And luckily, it's not going to be raining apparently either Tuesday or Thursday, so that's unusual. When you do anhydrous reactions, usually it's raining. Make sure you read experiment 8 very carefully. There are a lot of steps in experiment 8. If you need to read it, make your own outline of the steps. There's a lot of words and a lot of things covered in the pages with the experimental, so read it very carefully. You'll have a quiz as usual this week, and your experiment 6 report is due this week, so make sure you bring that with you. Next week, your experiment 7 report is due, so we're in this pattern of 1 week after another, we're going to hand things in. Also, next week in lab, you're going to be doing experiment 11 with your experiment 8 product. So we'll talk about how that's going to be work out for you, because we may be finishing a little bit of 8 next week before you do 11. I have posted, so here is what it looks like, the standard IR for polystyrene. It's on Moodle. So this is what you're going to compare your polystyrene IR to. It's also posted in the labs. You do not need to make a copy of it, okay? So save some trees. We all know what it looks like, and you're all going to use the same standard IR spectrum. So don't make a copy of it. Compare the peak list to your peak table and put it in your peak table for your report, okay? But don't make a copy of it, all right? You also this week will get GPC data that you need to analyze for your experiment 7 report, okay? Now here for registration, which takes place next week, so I'll say a few more words next week as well. For organic lab in the spring, there's two parts to organic lab. There's Chem 256A and Chem 256B. So Chem 256A is the first half of the semester. Most people that need to take organic lab for first semester need to take Chem 256A second semester. Okay? So it's very similar. It'll be your same lab manual. The experiments are in there. We'll do more detailed, more involved experiments with more involved analyses. But that's typically the part of organic lab that you need for degrees or health professions or whatever your track is. Chem 256B is an independent project, so not in your lab manual, where you will decide what your target compound is. You will propose a 3-step organic synthesis for it, and then after spring break you will try and synthesize your compound. Usually it is a research topic or has to do with organic lab curriculum. It is a way to get experience with research in the organic lab setting. If you're not sure if you'd be interested in research or not, it is a way that's pretty like safe way to try organic or try out research, because it's only a half semester commitment versus if you commit to someone working in their lab for a whole year or something like that and find out you don't really like doing research or do it for the summer and don't really like doing it. So it's a way to try out research. It's also a way for BAs in chemistry. You need another lab credit beyond 256A, so it's a way to get that lab credit. Most students that have participated in it said it's a good experience and a good way to get that research-like experience, okay? So please consider, definitely if you need organic lab in the spring, you're going to need 256A, but also please consider 256B. For 256B, if you are thinking of doing it, we need to know numbers, so go ahead and register for it. But you're not committed in stone to it, but it helps us know what numbers to start thinking about for that part, okay? So if you're thinking about it, register for it, and that's 1 credit as well. Okay? And like I said, if you have questions or things come up, we can address those next week. Okay? All right. So today we're going to talk about Grignard reaction. And this is a fairly important organic reaction because of the uniqueness of it. So it was found, it's named Grignard, so you always capitalize Grignard because this is a guy's name, okay? Victor Grignard is who discovered the reaction in the 1900s, early 1900s. And what this reaction involves, something that you haven't looked at so far, is something where we're going to use organic chemistry and we're going to use a metal in our organic chemistry. So it's an example of organometallic chemistry. And more specific, we're going to make an organomagnesium. So there's our metal, our magnesium, bromide, or it doesn't always have to be a bromide, it can be another halide, but typically they are bromides, okay? So the first thing we have to make is what is called our Grignard reagent. And we're going to take our alkyl bromide. So you guys on your reaction sheets from last week, you have a specific alkyl bromide that you're going to be reacting with magnesium. And our reaction is going to take place in ethyl ether. And we'll talk here in a little bit about why that solvent is important. Typically, Grignard reactions take place in ether, THF, solvents like that, okay? And what you are forming is this. Our magnesium basically inserts between our halogen and the alkyl portion of our alkyl bromide, okay? And why this is important for reactivity is what you get, we've got our carbon here, and we've got our R groups off of here. We've got a couple R groups, and these R groups could be H's or they could be other carbon groups off of it. But then when we get our magnesium in here, what type of charge usually do metals have? Positive. So we've got a partial positive charge on our magnesium. So what's that going to give on our carbon? Partial negative. So we've got a situation here where carbon is going to actually act like a nucleophile, which doesn't happen very often in organic chemistry. And so that's what makes this reaction important, because we can use carbon as a nucleophile to react with other carbon species, okay? And it's, you know, it's not like nucleophile like a chloride ion or a bromide ion nucleophile. But it is reactive enough to react with other weak bases. So for example, it'll react with water, which we'll talk about here in a little bit and why we don't want that to happen. It'll react with other alcohols. We can get it to react with aldehydes. We can get it to react with ketones or amines. So it is fairly reactive for specific species. And because of that, we can then use this to make a carbon-carbon bond. So that's another thing that doesn't happen super easily in organic chemistry, is making carbon-carbon bonds, okay? So it's a pretty important reaction as far as organic chemistry is concerned. So an example with just, instead of our R groups, let's say we have 1-bromopentane. React that with magnesium. Oops. Backwards here. we get, I'm going to erase our water because it's kind of in the way here. Oops. There we go. This is the magnesium bromide we would get out of it, okay? So when you guys are writing your reactions, you're going to need to show what Grignard reagent you're forming with your alkyl bromide, okay? Now, the reason that we use ether is for it to coordinate with the magnesium. So we need it to be able to solubilize that magnesium so that it can react with our alkyl bromide, all right? And ether solvents are good at that. Ethyl ether is good at that, so is THF. The other thing that is helpful about ether is since it is so volatile, it helps keep oxygen out of our reaction. And we'll talk about here in a minute why that is important. So that's why we're using ether instead of using THF for our reactions, okay? And it's that volatility giving it a greater vapor pressure, so the ether vapor sits above the ether solvent and helps push the oxygen out. Now with our Grignard reagent, we have to be careful of some side reactions. One of the first ones is the Grignard reagents love to react with water, and we don't want that to happen, okay? And when we do that, or when it reacts with water, these are the species we get. It kills our Grignard reagent and it's no longer reactive. So we get the resulting alkane from our alkyl bromide. It's now not going to react the way we wanted it to, okay? So if we get our Grignard reagent from reacting with water, that's trouble. We've now killed it and it's not there to then go on and do the Grignard reaction. So, a couple things we're going to do. We're going to use dry ether, and this dry ether is in the reagent hood. It's not in a red can, okay? So for setting up the reaction, we're going to use dry ether, and we're going to dry our glassware. So that's why for the AM labs, we're going to get glassware in the oven at 7:15 Tuesday and Thursday morning. And the PM labs, we're going to put glassware in the oven at 12:45 so that we can get our glassware dry in time for you to be able to use it. Okay? The next reaction is then its potential reaction with oxygen. So we talked a little bit about that. And so this is the species we would form, again, not our Grignard reagent. So it's not going to react like a Grignard reagent anymore. We've now inserted oxygen in there. And so this is beyond it being able to react as a Grignard reagent. What we're going to do here is we're going to use cotton balls in the openings of the glassware that are left open when you set up your reaction. So I'll show you here in a minute your setup. We're going to cover the openings with cotton balls to keep that exchange of oxygen back and forth at a minimum and help use the vapor pressure of the ether to help keep the oxygen out of the reaction. Now another thing we can have happen is our Grignard reagent can react with more alkyl bromide. So if we've formed this Grignard reagent, it can go on and react with alkyl bromide that has not reacted. And what you get is basically 2 times the chain length of the alkyl portion. So like in our bromopentane, we then get decane out. okay? And so then that kills off our Grignard reagent plus magnesium bromide. So what we are going to do to prevent this from happening is we're going to add our alkyl bromide dropwise. So you don't want to add it into your reaction all at once because of this problem, but also because your reaction is going to get super hot really fast, okay? So we need to add our alkyl bromide dropwise. That will control this problem. It's also going to control the heat of the reaction because we've got actually an exothermic reaction taking place. And you want to, even when you don't have it acting super hot, you still want to add it dropwise, okay? So that we don't get too much of this in the presence of our Grignard reagent, that it wants to react with each other instead of going on and reacting with what magnesium is left. So the setup you guys are going to use is glassware you're familiar with. It's just put together in a little bit different way than you're used to seeing it, all right? So you will have your round bottom flask with your stir bar in it. And it doesn't matter, I know your lab manual says 500 ml round bottom flask, but 500 or 250, perfectly fine, either one of them. You're going to clamp your round bottom flask right on its neck. Make sure it is clamped well. This apparatus, we're going to move up and down a lot, depending on what we're doing with heating throughout the process of the Grignard reagent formation and the Grignard reaction. Okay, so you want it clamped well here. You also want a support clamp on the condenser, but you don't want it to be tight because you need to move your apparatus up and down. Okay, you're going to have this set up above your stir plate, but what you want is space to put your hands under there. Okay, the reason for that, what's the boiling point of ether? 34, right? Really low. So with warm hands, you can warm your flask and actually start warming it enough to start refluxing the ether and get your reaction going. So you're going to want enough space between your stir plate and your reaction flask that you can stick your hands under there to warm up your reaction. Okay, so you don't want it sitting right on top of your stir plate. All right. Then you're going to have your separatory funnel on here. Remember, when we go to put things in the oven, no Teflon pieces from the separatory funnel in the oven. Okay, no, the stopcock will melt in the oven. All right. Stir bar's okay. No Teflon pieces from the separatory funnel. Then you're going to have one of your stoppers on one neck of the flask, and then this is where we're going to stick our cotton. Okay, in the top of our separatory funnel and the top of our condenser. All right. And you don't want to like wedge it in so much that you don't have. This is going to be how your apparatus isn't a closed system. Okay, so don't pack it in so tight that you make a closed system. Just put a piece of cotton in each that'll fit appropriately. Okay, so it won't fall in and stay at the top there, but you don't want it in so tight you've closed off the circulation of your system. All right. Now, when you go to get your glassware out of the oven, it's really important. You're using ether, okay? And we've talked about the boiling point is 34 degrees. So you have to let this glassware cool to room temperature before you introduce any ether into it, okay? Otherwise, if it's not at room temperature, you're going to immediately start boiling your ether, which you don't want to do. You're going to start with magnesium down here, and so you're going to have to calculate. We're getting tricky on you guys now. We don't tell you how much magnesium. You have to calculate the amount of magnesium. So make sure you show that in your pre-lab. Certain amount of magnesium down here, okay? And you're going to have 10 milliliters of ether in here. Now remember, where does the ether come from? Reagent hood, not the red can. Okay, this is our dry ether. Then over here, we need our alkyl bromide and 40 mils of which kind of ether? Dry ether, right? No red can ether, okay? Not yet, all right? You're supposed to make a solution of your alkyl bromide. An easy way to make a solution is put your ether in. Remember, stopcock has to be closed or it's all going in. Put your ether in first. Then add your alkyl bromide. It's more dense than the ether. It will go through the ether and want to go towards the bottom of the sep funnel. That mixing will be enough for you to have a solution of your alkyl bromide and ether. So you don't want to try and, get an Erlenmeyer flask out and make the solution or anything like that. We don't want to undo the dryness of the ether by trying to make the solution. Just add the ether first and then add your alkyl bromide. Then you've got your solution, okay? At this point, we are going to come around and check your setup, okay? And a lot of us will probably be adding that 5 ml portion from the sep funnel that your lab manual talks about. Will help you get the iodine in there and will help you get this reaction going, okay? Now what you want to watch for with this is changes in the reaction. So magnesium is a silver metal. Iodine, what does iodine look like? Orangish red color, right? So when you put iodine in there, you're going to see an orange-red color. You should start seeing bubbling on your magnesium from holding your hands under your reaction. You should start to see some cloudiness. You should start to see some of that color of the iodine fading. That means your reaction started. Then you want to start adding that alkyl bromide dropwise, okay? And you want to keep it refluxing. You want to keep it under control, but you want to keep it refluxing while you're adding that alkyl bromide, okay? All the while, have you turned on your stir bar yet? No, do not turn on your stir bar. Because if you do, you'll kick up the ether vapor and you'll start drawing in the oxygen that we've been trying to keep out of your reaction and the moisture we've been trying to keep out of your reaction, okay? So no stirring during the Grignard reagent formation. You want to add your alkyl bromide dropwise, but keep the contents of your flask refluxing. You don't want it to stop. If it stops, it's hard to get it going again, okay? So you want to keep it refluxing. At any point along the way, if you are not certain what should be happening here, things don't look right, grab your instructor so they can look at it, okay? Big important things though. The reaction of your magnesium and your alkyl bromide. If you add neat alkyl bromide to your magnesium in ether, very exothermic reaction will happen very quickly. Your ether will get very hot and start boiling away. And what is a problem with ether because it's so volatile? Things that are volatile can also catch on fire, right? So we don't want any fire, okay? So no neat alkyl bromide going in on your magnesium all at once. That's why we make this solution here, okay? And that's why we have you add the ether first. That way, if our stopcock isn't closed off, at least we've got only ether in there and not alkyl bromide, okay? So this alkyl bromide always goes in dropwise. We don't want any exciting moments in organic lab this week, okay? Because it will be. It'll be exciting. It would involve 2 condensers and all sorts of things. We don't want to do that. So be very careful with this setup and follow the instructions very carefully. Okay. All right. So then when we get done with adding our alkyl bromide, we still need to keep that, we want to keep a reflux in that flask. We're not stirring yet, okay? Keep reflux for about 15 minutes, okay? If your reaction is still refluxing after you've added all the alkyl bromide, don't put water underneath it immediately because you'll kill that reflux, okay? Keep it refluxing, and if you need to use hot water, then do so as you need it because the reflux has stopped. But don't throw water under it right away because you will kill the reflux right away instead of letting it go its own natural course, okay? So we want about 15 minutes, and we want to try and keep it refluxing for that 15 minutes. We are still not stirring, okay? No stirring yet, all right? Okay, the next thing we've got to do is look at our Grignard synthesis, right? One thing I forgot to mention, so what does the iodine do for your magnesium? Anyone catch that? Your magnesium has oxides on the outside just from it being exposed to air. The iodine helps clean the surface so that you get rid of those oxides and help clean it so it's ready to react, okay? So another note with that, our reagents we want to keep completely dry. That means keep them completely capped. Our magnesium is included in that. Don't leave it open to the air because then you've just got your magnesium, the bottle of magnesium sitting there reacting with the air, okay? So it'll make it harder for the next person's Grignard reaction to get going. So keep everything capped once you are done using it in lab. Also be careful with the magnesium. It potentially is a flammable metal, so we don't want it just, spread out all over the balance. Be careful when you are weighing it as well, okay? All right, so our Grignard synthesis. We've got our Grignard reagent. It is sitting in your flask. And hopefully what you have noticed is changes in what it looked like from the start. You should have less magnesium than when you started. Okay, so that's one thing that you should know. Now we're going to react our Grignard reagent with our aldehyde. So again, look at your sheet of paper, make sure you're using the aldehyde that is on your sheet of paper. Those aldehyde solutions have been made specifically for the amount of how many of those sheets of paper had that specific aldehyde on it, okay? So you can't just use a random aldehyde, otherwise you're going to be using someone else's aldehyde. We're still in ether, nothing has changed. So remember, this carbon now has some nucleophilic character, so it can actually react with the carbon of the carbonyl that is got some electrophilic character, okay? And so what we form is this tetrahedral intermediate, which are always important in organic chemistry. And now, here's our partial negative charge, and our partial positive charge is still on our magnesium, okay? At this point, we don't have what we want yet. We have to do another step, which is going to be involved in the workup, okay? So we don't want to isolate our intermediate here. We want the alcohol at the end. So what we need to do is we're going to use acid, and in our case, we're going to use sulfuric acid, okay? And then we will get our alcohol. Okay, so it's important to note here where each carbon chain is coming from. So this guy came from our alkyl bromide, all right? This carbon is the carbon of the carbonyl of your aldehyde. This alkyl chain is from your aldehyde, okay? So the other part of your half sheet of paper is you have to draw the structure of your product. You have to predict what your product is. So make sure that you do that correctly as well, so you know what you are making. We want to stop here, okay? But it is really easy to get to here if you heat up this step too much, okay? So we're first going to be adding our aldehyde to our Grignard reagent. This again is going to be dropwise, okay? So make sure when you go to put your aldehyde in your separatory funnel, you've got the stopcock closed. This aldehyde solution is already prepared for you, okay? It's 25, you're going to measure out 25 milliliters of the appropriate aldehyde solution. Make sure you read the labels carefully. There's 4 alkyl bromides, 4 aldehydes, so you got to make sure you pick the right one. Then when we get to this step, you're adding sulfuric acid dropwise as well. You don't want to reflux your ether during this addition because then you will start making the elimination happen, and this is what we want to see in experiment 11. We don't want to see it yet, okay? So this is our experiment 8 product. We don't want this one until next week, all right? So control the addition of your sulfuric acid so you don't get the elimination product, okay? So a couple things also with this aldehyde addition. Right before you go to add the aldehyde, guess what you finally get to do? Stir the reaction. We finally get to turn our stir bar on. Right before you add that aldehyde. So when it's in your separatory funnel, your stopcock is closed, you're going to start stirring the reaction, and then the aldehyde is added dropwise. What kind of bath do you have around your reaction at this point? Cold water, okay? Now what we don't want is ice water. Ice water is too cold, all right? So you're going to put a cold water bath. So after your 15 minutes of reflux, you let it cool to room temperature, then you're going to put a cold water bath around it. Don't use ice water, okay? Cold water. Now, you may see some interesting things with this aldehyde addition. It can sometimes pop. It can sometimes levitate the cotton. All sorts of interesting things can happen with the aldehyde addition. So just make sure you're controlling it. We're still controlling it and adding it dropwise, okay? But if you hear some popping noises, that's okay. If it kind of levitates your cotton a little bit, just stick the cotton back in the condenser. Just make sure you're not adding it too quickly. Okay? If you add this too quickly, what can actually happen is you get the ketone of your alcohol to form. So you don't want that to happen either. That's a byproduct that you don't want. So if you add the aldehyde too quickly, you get another byproduct in your mixture that you don't want to see. All right? And we're going to be analyzing these reactions, experiment 8 and 11 with GC, so we're going to see what's there. Like any impurities, we'll see them, we'll see what's going on there, okay? Including the ketone, and if you make it in 8, you don't get rid of it in 11. You're going to see it in 11 as well, okay? So just be careful with this addition. When you are done with the aldehyde addition, then you're going to stir at room temp for 15 minutes, okay? So just remove your bath, stir it at room temp for 15 minutes. During that time, then prepare your sulfuric acid solution, okay? Then, with the sulfuric acid, you're going to add that dropwise, okay? And there's a couple different things happening with that addition. The other thing when we're adding this is we're in an ice bath. So now we will use an ice bath, okay, because we don't want this getting hot. The other two additions, we're letting things reflux. This one we don't want to. So there's multiple reactions that are taking place during the workup. One of them is what we're trying to do is get our alcohol to form. Okay? So So we're getting our alkoxy magnesium bromide to react with the acid, and we want our alcohol plus then some magnesium bromide that's floating around in there. It'll pick up a counter ion somehow, but it's all positively charged anyway because of the acid. The other thing that'll happen is if we have any Grignard reagent left over, we're going to kill that because we're adding water and we're adding acid. So the same as what we showed up there with it reacting with water, we'll kill our Grignard reagent. And we've got this guy, okay? Also, that magnesium that's left over is going to react with sulfuric acid. So this is actually a displacement reaction from GenChem. We'll make magnesium sulfate plus hydrogen gas. So you're going to see some bubbling. That is the formation of the hydrogen gas. Okay? And basically, we want this bubbling to cease before we can proceed. Okay? So we don't want this reaction to keep going once we transfer things to a separatory funnel. So once you've added all of the acid, you're waiting for this to be ended before you transfer to the separatory funnel. Okay? Now, this magnesium sulfate is a white solid, so what you may see, depending on how much magnesium you have, as you're adding the sulfuric acid, things are getting kind of thick with solid, and you're seeing visual evidence of that solid forming. Don't worry about it until you get to the end of the addition, okay? Because what sometimes will happen is it'll look like you're getting tons of solid, but then as you add more sulfuric acid, things get more solubilized, okay? Because it talks about in your lab manual you don't want to add any solid to your sep funnel, which is true because you'll clog your sep funnel. But with this magnesium sulfate, wait until you've added that sulfuric acid to make a determination if you've got to do something with it. If you still have white solid after you've added all of the sulfuric acid and let it stir for a couple minutes, then you're going to add a little bit of water, and so follow your lab manual for that. You just need a little bit of water to make that salt soluble, okay? So once you're all set with this workup and all of the bubbling that's going on, and here while I'm something to help you with your pre-lab, put this up while I show the rest of it. So in your lab manual, we give you it's kind of a complex flow chart for this experiment. So we've given you the flow chart for the workup of the reaction, okay? So we're basically to this point here where we have added our sulfuric acid, and now we're going to get to the point where we're going to separate the two layers. So we're going to separate our two layers because we've got an aqueous layer and we've got an ether layer in our separatory funnel. So our separatory funnel isn't just an addition funnel for your reaction, it's also going to be used in the workup. There's two different things that you are going to use then with both of those layers, okay? So we are going to extract the aqueous layer with ether. So what that means is you are going to have your aqueous layer in your separatory funnel. You're going to add ether to it. You're going to shake and vent it, and you're going to separate and drain off the aqueous layer. That is what is meant in that word extract. Okay? And when we say extract, we are trying to get something out of, layer with layer here with ether. We are trying to get something out of that aqueous layer that we want. That's why we are extracting with ether. We're making sure all our product is out of that aqueous layer, okay? So again, with extract, aqueous layers in the separatory funnel, ethers in the separatory funnel, shake and vent 3 times. Let the layers separate, drain the aqueous layer, then you have your ether layer. That is all meant in extract, okay? Then we're going to wash the combined organic layer. So we'll take this ether layer with our original ether layer. We're using 5% sodium bicarbonate. The reason for that is we don't want any acid before we go do the distillation, because if we have any acid present, we'll do the elimination reaction. We'll keep going to experiment 11, and we're not ready to do that yet, okay? So wash means we'll have our combined ether layers. We're going to add sodium bicarbonate to it. We're going to shake and vent 3 times. We're going to drain the layers, or drain the aqueous layer, and you'll have your remaining ether layer. That is what is implied in wash, okay? And by washing, we're taking what we want and getting out the things we don't want, okay? So once you have done these 2 steps, then we're going to add a new, so we've got extract, wash, and then we're going to dry the organic layer. So that's your ether layer, which should be which layer, top or bottom? Top layer, right? Ether's less dense than water. With anhydrous, so we already talked about magnesium sulfate, but we need anhydrous, so dry magnesium sulfate. Dry magnesium sulfate looks like cooking flour, okay? It's really light, floaty. What you're going to do is you're going to have that magnesium sulfate. It reacts with water in your organic layer and complexes with the water, hangs on to the water for you, okay? So this is like floating, free-flowing when you put it in your flask, okay? When you get it wet, it makes clumps. So what you want when you add magnesium sulfate, you're going to add it to your organic layer and swirl it around. What you want to see when you swirl it around is some clumps with a little bit of free floating. That means you've got enough in there. If you only have clumps, you potentially haven't dried all the water out, okay? So what you want here is like the snow globe effect. You go to shake it, and you'll have some floating around like a snow globe, okay? Whenever you dry an organic layer, it's better to use an Erlenmeyer flask than a beaker. Then you have less flow back in of water, so use an Erlenmeyer flask for this. You're going to shake it around really well until you have the clumps with some free floating magnesium sulfate. And then you're going to put some saran wrap on it and let it sit for about 10 minutes, okay? And this is all part of the drying the organic layer, okay? Then you're going to filter off the magnesium sulfate with gravity filtration and rinse it with ether, okay? And one thing I forgot to mention here. When we get to the ether with extraction, what ether is that one? Red can, right? Same with here. When you go to rinse, even though we've dried things, when we go to rinse our magnesium sulfate and water complex, we rinse it with red can ether. Okay. That magnesium sulfate and filter paper, let it air out in your hood, and then put it in the waste bucket that's in the reagent hood, both the filter paper and the solid, okay? Because this solid, is it organic or inorganic? Inorganic, so does it go in organic waste? No. No magnesium sulfate in the organic waste, okay? So the filter paper and the magnesium sulfate go in the waste container, okay? So then what you have left is your ether layer. We need to get rid of our ether, so what are we going to do? What do we always do when we need to get rid of a solvent? Simple distillation, right? Okay, we've got lots of things to do this week. So one way to make our simple distillation, because we do need to finish this week, okay? We have to complete the simple distillation this week. You have to be through this part for next week. Start with hot water. When you've got your apparatus set up, leave your condenser set up because you're going to use it again. As you are drying your organic layer, get your simple distillation set up, okay? We're going to use a hot water bath because we just have ether to take off, okay? And you're going to distill until you don't have any more ether coming off, all right? So first part is a simple distillation. Then your lab manual talks about a fractional distillation. This is where we're going to use our all-in-one simple distillation apparatus, and we're going to collect anything that boils below the boiling point of our alcohol as impurities, and then we'll collect our alcohol at its given boiling point, or you're going to start about 20 degrees below its boiling point, okay? Key with this guy is your boiling point of your alcohol is for sure greater than 100 degrees. If you have made the correct compound that was on your half sheet, it is greater than 100 degrees. So be careful when you're looking up the boiling point of your alcohol. A lot of times they'll be listed as something lower than that, but then it'll say like 20 millimeters of mercury next to it. That means it was collected under vacuum, not at atmospheric pressure, okay? So you need to find the atmospheric boiling point of your alcohol so you know what you're looking for this distillation, okay? This one has to happen this week. Your fractional distillation, we could do next week before we start experiment 11. You will have time to do it next week in lab, okay? So this, you have to get through this week before lab next week. This one you can do in lab next week, all right? After the simple distillation, you can store your product in a round bottom flask. Make sure you grease the stopper so it doesn't get seized, because there's still going to be ether in there that once it cools down is going to want to suck down on that stopper, and it'll be hard to get it off next week. Okay, so make sure there's a little bit of grease on your round bottom. You can store it in your round bottom flask in your drawer until next week, and then we can do this part. If you're very efficient this week and you get to this point, just make sure you double check with your lab prof as to what your boiling point is so that you are collecting your alcohol at the correct boiling point range, okay? A couple things we'll need for next week, so just keep these in mind. We eventually will need the yield of our alcohol. You're going to collect an IR spectrum of your alcohol, and you're going to make a GC sample of your alcohol, okay? And we'll talk about GC next week, okay? So if you got through this part, you could do this one, and you could do this one, all right? GC samples will come next week, okay? But these are the three pieces we're going to need, okay? All right, make sure you read things carefully and listen. Go through these things carefully. And I think someone's coming to make another announcement.